Okay. Okay, so King County sort of laid out marine monitoring for sort of their region, and I would like to introduce now Ecology's marine monitoring program and the trends and pattern that we find in there. Oh, people are coming back. That's great. Thank you. Below is my team. Some are in the room here. And so I would like to start that ecological systems show variability on different spatial and temporal and organizational scales. And so what that means is that on one scale you might see pattern and phenomena that you don't see on a different scale. And within Puget Sound we have different monitoring programs for the marine environment that have certain objectives, and they are good in detecting certain patterns and trends that others don't. So we sort of try to work collaboratively to really sort of get at the story. So I would like to show the results from Ecology, and you see sort of on the left side our marine monitoring station network. We have like a network that we cast from Olympia to the Canadian border. We also have stations in the coastal bays. So the strength of the program is really at long-term trends and the impacts of large drivers such as climate change, hydrological cycle and human pressures on the entire system. So we sample the station network monthly. We use a float plane or a boat and lower a CTD package from it all the way to the bottom. And we'll look at sort of long-term trends in water quality and with a specific focus on eutrophication. So we measure a suite of physical, chemical, and biooptical variables to sort of place these observations and trends into the context of large-scale drivers, estuarine circulation, etc. And so we have to deal with extremely large variability. So there is great variability spatially from basin to basin, and there is great temporal variability through seasonality. And that is confounding our trend analysis. So how do we deal with that? Well, we have a long-term data record from 1999 to present that is very consistent. So we kind of know what to expect at each time of the year at each station. So we can ask the question, relative basically to that time of the year, is a station behaving above, below, or expected ranges in the data? And so effectively that allows us to compare very different regions and ask the question, are there sort of large perturbations going through the entire system that we pick up in all stations? But it also effectively removes seasonality because we sort of taken the seasonal cycle out. And that allows us to aggregate the information together and ask the question, is the interannual variability how the entire system is sort of responding to potential drivers? Okay, so we do water column monitoring. We also focus on the surface where a lot of the action is happening. We use en route ferry monitoring, here like the Victoria Clipper that goes between Seattle and Victoria twice daily. And we have a program called Eyes Over Puget Sound in which we qualitatively describe large blooms, oil sheens, and sort of large features that we see in order to create awareness in the community and also sort of deliver material for outreach and education. So all the data that I'm going to be showing are sort of trend analysis in anomaly space. So keep that in mind. Okay, so I would like to start with a very simple story first. So looking at conventional water quality indicators, and Stephanie sort of laid this out very nicely. So when we look at nitrate, for example, in the upper graph, and sort of look at the trend from 1999 to present, we see sort of an increase in nitrate in our entire station network relative to expected values to up to like 2008, and then they start to decline again. So I added 2 red dots because these were like the 2 extreme years with the blob and El Nino, and sort of I'm trying to highlight because we learned something from these perturbations that were on a very large scale. When you look at depth integrated chlorophyll anomalies from the surface to 50 meters, we see a decline of chlorophyll that is sort of continuing over the last 17 years. And when we look at oxygen at greater depth, 20 meter all the way to the bottom, and here we sort of massage the data into a depth integrated variable, the oxygen deficit, then we don't really see sort of long-term trends. There is sort of great interannual variability initially, but the trends are not really there. So at first glance, when you look at sort of classical water quality indicators, this sounds like a success story. Nutrients are beginning to go down, chlorophyll is going down, it's all great. So the big question is, are these physical processes, are these ecosystem processes that are driving that, or is this really a human success story? So what I would like to do is sort of first lead you up the wrong way and then show you that we're actually missing a lot in that story that sort of becomes apparent when we sort of really dig deeper into the data set. So let's first start with a sort of a conceptual diagram of Puget Sound. Puget Sound is a deep fjord, so it has sills that prevent the exchange with the ocean. But we are very fortunate because we live next to a very productive upwelling system. And so upwelling systems have the benefit that they have a short, productive food chain based on diatoms. A lot of energy is channeled high to higher trophic levels very fast, and commercially we exploit that. So in Central Sound, here sort of in the middle indicator, we sort of can benefit of that upwelling by bringing in that upwelled water that is typically very high in nutrients, it has cold temperatures, it has the disadvantage to be lower in oxygen and has a lower pH. But when that water makes it to the surface, it has sort of a kind of more natural nutrient cocktail that gives rise to a lot of productivity in Central Basin, in the form of diatoms. And that's something that we all cherish because that sort of sustains a lot of fish. And we saw that from King County. So when you have diatoms, you know, they tend to be heavy because they have silicate. So once they die or get consumed, that material can sort of trickle down through the water column very quickly and reach the bottom. And so that is our classical sort of understanding of Puget Sound, that when you sort of increase the nutrient pool by now adding human sort of nitrogen to the surface, then you increase that organic sort of export to greater depth, and the result is that you sort of draw down more oxygen in addition to already low oxygen that you get in from the ocean. So what is driving that water exchange? Well, here the timing of processes is very important because it so happens that most of the fresh water is delivered into the Salish Sea basically in early summer. So June is sort of the peak flow, and it's the Fraser River. And that sets in motion an estuarine circulation with sort of a net flow of water at the surface out of Puget Sound into the Salish Sea, and an inflow that brings in that upwelled water into the basins and sort of provides the benefits of an upwelled system. So to just give you sort of an idea what the nitrogen loading is, I take some numbers that I got from the modelers at Ecology, and sort of the ocean has about 90% of the nitrogen loading. So that's a big gorilla. So any changes in that exchange might be very important. The contribution from rivers and sort of human inputs is about 10%. And so the key message is when you have sort of a turnover and renewal of water, because you have high summer flows, then the additional nutrient additions don't matter as much because you import a lot of nutrients from the ocean and you sort of wash that out at the surface. So but climate has been playing us a curveball, and I would like to sort of indicate that here, in that specifically in the last 2 years, the snowpack melts prematurely. And so what that does is it sort of separates two processes that used to be sort of in sync in time. And the upshot is that estuarine circulation is weaker in the summer months. So you still have upwelling along the coast, but now you don't have the freshwater contribution that really drives estuarine circulation as strongly. And so what that does is sort of it reduces the natural sort of gorilla in terms of nutrients from upwelling. And at the same time, the water sits there for much longer. So the last 2 years, we saw much warmer temperature in Puget Sound. That's also a result that the water resided much longer. And when you have water sitting there much longer, you also have a greater burden of human inputs over time. And so that might change potentially something in the system. And so what I'm proposing, and I'm going to show you some data, is that you change the base of the food web. And when you change from diatoms that tend to be heavy and export a lot of material to species that are sort of more regenerating nutrients at the surface and more quickly, then you change the entire sort of nutrient cycling in the system. and also sort of the outcome of oxygen at depth. Okay, so what data do we have to support that potentially? So this is the Fraser River. It's the largest contributor to the Salish Sea. That river drives most of the estuarine circulation, bringing in sort of the upwelled water into the Salish Sea. These are 3 years, 2014, 15, and 16. The climatology is the black line. Here superimposed in color are the actual flows. Blue are higher than expected, red lower than expected. You see that most of the discharge occurs around June. That's the freshet. And the last 2 years, 2015 and 16, showed sort of reduced summer flows of the Fraser River. So 15 was the blob, 2016 was the drought in BC. So there are sort of effects that are actually larger than just Washington that affect sort of the exchange between the ocean and Puget Sound as well. So what I want to point out is sort of the match with upwelling. So in green, I superimposed at the bottom positive upwelling along the coast, here indicated with the upwelling index. And so you see that in relation to the climatology, these processes are more in sync in time. But when you have a premature sort of melting of the snowpack, you begin to sort of separate these processes in time. Okay, so why is this potentially a big deal in the future? When you look at the climate change impact report in 2014, the predicted flows of the freshet are sort of moving several months earlier into the season, as indicated in the middle graph here at the bottom. Black is sort of the historical discharge of fresh water, and then you're moving to a sort of earlier and earlier discharge here indicated with dotted lines into the future. Spatially, that also pans out on the right lower level are the sort of predicted 50% reductions in summer flow. So there's potentially sort of a big impact coming our way, just driven by climate. And so that separation of processes is probably going to be something that we see much more often, even though we sort of got a glimpse of that the last 2 years. Okay, so let's look at the nutrient pools again. So let's revisit nitrate. So the nitrate anomalies here over the last 17 years show sort of an increase to 2008 and then a decline. But that includes basically the whole exchange between ocean, Puget Sound, and the Salish Sea as well. And so the ocean is the big gorilla. So what can we do to potentially take that ocean out and just look at sort of the effects that we have more sort of locally from Washington? The ocean has one big advantage, it has salt. And so we can use salt as a passive tracer. So if we know the ratio of nutrients to salt that makes it into Puget Sound, we mathematically can remove that and sort of look at nitrogen trends with the ocean signal removed and the variability. So when we do that, here on the lower graph, we see sort of a consistent increase in nitrogen over time. Doesn't mean it's a human impact, but just at sort of on a statistical level, there is sort of this increase in nitrate over time. And this includes sort of effects of biology, because these are sort of inorganic nutrients that we measure. So there's a large fraction actually that is also sort of be packed into organic material through primary production. Okay, so what indications do we have that this could be eutrophication? And I would like to open this up for a discussion. The silicate to nitrogen ratio is sort of a putative ratio in the literature that indicates that you have human nitrogen inputs dominating the system or influencing the system, because we sort of introduce nitrogen disproportionately higher than silicate. That's something that Stephanie also mentioned. So when we look at sort of the Puget Sound-wide interannual trends of silicate to nitrogen, we see in the upper graph sort of a decline over time that's significant. So there's a change right there. And the silicate to nitrogen ratio is also sort of a measure potentially that can affect the phytoplankton community structure. So either through limitation of silicate, or in the other case, you introduce nitrogen that has potentially a very different sort of quality that gives rise to more nuisance species in the system. So it has the ability to affect the base of the food web. So remember, sort of, I said potentially if we change the food web at the surface, we also change how organic material is sort of exported to greater depth. And that's very important in a fjord system because fjords are deep, so it matters. Chesapeake Bay, it wouldn't matter so much, but in Puget Sound it does. So we don't unfortunately have sediment traps out there, but we have chlorophyll data. And so we can ask the question, how does the chlorophyll near the bottom in relation to the surface change over time? So we basically, at the bottom, we still find small concentrations in chlorophyll, and so we saw a seasonality on that one. And so that sort of prompted us to investigate how does that coupling between the surface and the bottom really change over time. And so when we plot the data in anomaly space in a similar way down here for deeper stations greater than 50 meters, we see sort of a decline in that ratio. So that means that less phytoplankton is making it to the bottom. So that's just fresh material. It doesn't look at organic material and particulates that don't carry chlorophyll, but the freshness, the quality already changes. And keep in mind, I showed you a graph how chlorophyll decreased over time too. So effectively, the amount of fresh material that makes it to the sediment has changed in the last 17 years. Okay, so what other indications do we have potentially of eutrophication? There are sort of reported nuisance species in the literature. One is Noctiluca dinoflagellate. We sort of documented with eyes over Puget Sound. Qualitatively huge blooms in Central Basin. We saw a lot of jellyfish, also a eutrophication indicator. We saw a lot of dinoflagellate blooms on a massive scale. And we see a lot of macro-algae rafts drifting through Puget Sound that wash up on the beaches. So what they all have in common is they float at the surface. And so they escape sort of conventional monitoring programs. So that's a large sort of amount of organic material that's kind of a blind spot, but they are sort of indicators of eutrophication. Okay, so I want to show you that these trends are not occurring sort of randomly throughout the year, but there is a certain window in the summer months that basically these trends are sort of stronger in our data set. And so I'm using a bubble plot. And the size or the sphere of the bubble is proportional to the percent change for each month. Filled dots are positive changes. Empty dots with a negative sign are sort of negative trends. And so I would like to point out that the non-oceanic nitrogen and phosphate is sort of changing in the summer months, sort of the first two rows. The ratio of silicate to nitrogen is really sort of plummeting strongly in the summer months. Ammonium has been picking up also in the summer months, which is an indication of potentially more nutrient regeneration through the microbial food web. Chlorophyll has slightly decreased also in the summer month, and sort of the connectivity between the surface and the bottom, that flux has also decreased in the summer months as well. So what's so special about the summer months? Well, I would like to sort of bring up a study or a report by Tezin. She's sitting over there. I keep sort of quoting that a lot because I really like that figure. So she was looking at the nitrogen loading wastewater treatment plants relative to rivers in Puget Sound over time. And so the upper plot, you see basically that wastewater treatment plants here in blue are discharging at a constant rate, whereas sort of the nitrogen loading coming in from rivers has a strong seasonality. And it so happens that during the summer months, the contribution from wastewater treatment plants is much higher than that of the rivers. So bear in mind, this is only 10% of the entire sort of nitrogen loading because we have 90% coming in from the ocean. But right at the surface, there's a seasonal effect where it changes, and potentially we have sort of a temporal window of greater vulnerability for human impacts. And so combine that with sort of the predictions of reduced summer flow and a reduction in nitrogen loading from the ocean because you slow down estuarine circulation, we potentially have sort of a greatest sensitivity in the summer months. Okay, in summary, so these are sort of my summary bullets. I just read them. The relative timing of the Fraser River and upwelling matters for the Salish Sea water quality. And so we potentially sort of have a land-ocean climate connection where we can sort of see potentially the impact, how large-scale climate signals translate through hydrological cycles into water quality. And so I think that's very powerful, and I think we should sort of pursue that more. The ocean is driving nitrogen, but when the ocean is removed, we still see sort of the increase in nitrate. And I think that's worth sort of discussing what that could be. At the same time, we see eutrophication indicators such as nuisance species. We see shifting in nutrient ratios in the system. And I think there's enough pieces of evidence that we should open our discussion. Export production during summer appears to change towards a more regenerative microbial food web. And that is very important because the microbial food web is sort of a big gap that we have in our monitoring sort of data. The microbial food web can channel up to sort of 50% of the primary productivity through a microbial sort of food web, and we have basically zero information on the rates over time and how that is changing. And so the last point that I would like to make is, even if we do sort of business as usual, sort of climate change might throw us a curveball, in that we have a change in the residence time of water, and we're going to hear more about that, that magnifies our impact in the future. Okay, so I showed you data, monitoring data, but correlations do not prove causation. And the other question is, well, if we see a statistical significant trend, does that actually mean something for sort of the ecosystem in general? And that's, I think, where sort of modeling is really strong, because they quantitatively can explore that much further, and we're going to hear much more about that for the food web and also for nutrient loadings. But I think we have enough pieces of information to sort of ask the question, maybe we should rethink how we sort of message, you know, sort of the ecosystem, and be more open towards, you know, acknowledging knowledge gaps that we have and sort of exploring mechanisms that might be driving these phenomena. And so what we've been doing is we sort of generated a conceptual model here, sort of this graphic that is kind of capturing sort of the essence of these ideas, and we back them up with testable hypotheses in the hope that we can sort of engage the scientific community to sort of explore this in much greater detail. And so here it goes. So in the middle you have sort of the short productive diatom-based food chain. Typically that's also occurring to the spring bloom. And if you have diatoms at the base of the food web, they tend to be heavy and have a strong coupling to the sediment and support sort of species in the sediment. And we're going to hear much more about that from Sandy Weekland. So if you change that and you have more like a microbial-based food web, where diatoms don't tend to be so important in terms of rates, not standing stock, but in terms of turnover rates, then you really change the entire sort of export of organic material. And that's very important, because you start to remineralize nutrients more in the water column. You don't export it to depth. That means the oxygen drawdown at depth is going to be reduced. You have that more sort of mid-water, and you keep the nutrients right at the surface so they get regenerated. And so therefore have that feedback on organisms. We see a lot of nuisance species out there that tend to all cannibalize sort of the classical diatom-based productive food chain. And so like Noctiluca and jellyfish both compete directly with copepods. And copepods are very important to sustain, you know, herring and sort of fish in the upper trophic levels. We also have evidence potentially from sediment cores. Jill Brandenberger's report looked at microfossils of diatoms in the sediment. She sort of detected a decline that started in the 1950s that has been going on. We might be just capturing sort of a part of a larger pattern that's been underway for much longer. So we hope that by basically providing testable hypotheses, trying to tell a story, we can engage, you know, people in a very sort of active dialogue to really get at the root of the issues that are pertinent to Puget Sound, and specifically sort of in context of climate change. Okay, and with that, I would like to open it up for questions.
Any questions out there?
If you don't have questions, I'm going to proceed to the coffee pot right away.
Okay. Oh, we've got one. So, can you hold just one sec? We need to put you on the mic. Thank you.
Hi, I'm Derek Day from the Department of Ecology. I only noticed at the last minute, but when you were looking at the wastewater treatment inputs, did those have seasonal trends, and what would drive those seasonal trends from wastewater treatment plants? I would assume
No, pink are the rivers.
The pink are the rivers, but they also look like bumps in the wastewater treatment plant. I'm colorblind, so.
We have an expert sitting here, right there. These are Tazine's data. Do you want to sort of...
Hold on a second, Daisy. We've got a mic on. So the answer was influent infiltration, rainfall events. Pipes are not 100% sealed proof, but yeah, it's not a seasonal trend in terms of wastewater being generated by people as much.
Okay, thank you. Oh, there's one in the back.
Hold on one sec till the mic. Wait a second. Can you hold your question just one sec? Peter.
I can't hear.
And ask your question.
Peter Murchie with EPA. So understand what your hypothesis is around the biologics cycle at the top. But when they die, where are they going? So that interaction at the bottom, I assume it's different because it's different material, but is it not going to the bottom at all?
Yeah, so the key word is buoyancy. So, or negative, or ballasting. So diatoms have a silicate frostule. So when they get incorporated into fecal matter of copepods, basically they can sink through Puget Sound like 100 meters same day. So basically, if you have diatoms, whatever is consumed at the top is basically consumed at the bottom pretty much the same day. If you have species that are like Noctiluca, or you have small flagellates, they tend to be more neutrally buoyant. So they sink very slowly. They also sort of tend to disintegrate much further. And so basically they spill their nutrients into the water column much higher. And so they don't have the same sort of, you call it sort of the benthic pelagic coupling. They don't have the same export as diatoms. And that's very important because when you remineralize it in the water column, you retain the nutrients up there and you don't export them to greater depth. And that also translates potentially into where oxygen is drawn down in order to remineralize that. So buoyancy, and that's something I try to stress. We are not in Chesapeake Bay, we're in a deep fjord. So knowing, how the sort of the sinking quality of your organic material is very important.